Now we're going to move on to the lightning poster session, which I'll introduce very briefly. We have 21 terrific submissions that cover a variety of topics. We tried hard to organize them, and in the end, we decided alphabetical by author last name, and we started at the end of the alphabet. So we just thought we'd give people a chance. So there's no particular order, but there's just some great work, and so each author is going to present a short bit, and then we'll have our poster session later today, where you can actually attend and talk with the authors. So you will go into these rooms through your Hop It platform, choose the posters. We're going to, sorry, that's how it works in the afternoon. We're going to get a little brief overview of each poster so you can decide where you want to go this afternoon. So I'll turn it over to the lightning poster session.
Hi, everyone. My name is Davide Sotara. I'm Principal Knowledge Engineer at Mayo Clinic. I represent the knowledge management and delivery team. Our team has been focusing on delivery of computable knowledge to providers at the point of care. So our latest application, called Mayo Expert Advisor, is a fully model-driven cognitive support application that combines a variety of CBKs ranging from computable guidelines to decision support, dynamic content, care processes, decision models, artificial intelligence, data, semantics, API integration. So it's a fairly complex application, and to build it, we've identified more than 20 types, 20 categories of CBKs, and we used more than a couple of dozens of knowledge representation, modeling, programming languages to build this fairly large knowledge base. So the focus of our poster is to present the underlying architecture, which is a foundational part of the application. And in the spirit of CBKs, we've used a knowledge graph approach to enumerate, relate all these CBKs, their types, their relationships, and the languages and the execution models behind that. So I'm looking forward to let you know more about this application, and thank you for watching me.
Hello, this is Pawan Goel with the American College of Emergency Physicians, or ACEP. I'm very happy to present you the poster on impact of COVID on emergency department visit volume and unintended consequences thereof. As we know that typically 140 to 150 million patient visits happen in 5,000 hospital emergency departments across the nation on an annual basis. COVID has really impacted the emergency department visit volume. While patients have been scared to come to emergency department for the risk of getting exposed to COVID-19, they have preferred to stay home and not to come to hospital. The visit volumes have significantly dropped. Some places it's as low as 30% and other 50% reduction in the volume. While this reduction is well understood, but there have been a lot of impact because of this reduction. Patients who critically needed emergency care, such as for acute chest pain leading to myocardial infarction or cardiovascular accident, such as stroke events, they have chosen to stay home and then suffer the consequences. The biggest impact has been on the geriatric population and the pediatric population on a nationwide basis. ACEP has a registry called Clinical Emergency Data Registry, or CEDAR, that captures more than 25 million visits every year. So we have been working with Yale University to analyze our data to really understand the impact of emergency department visit, various disease conditions, and various populations. And we will be happy to present some of those details to you through this poster. So please do stop by and visit our poster session.
Hi, I'm Erica Raznick. I'm a biostatistician and epidemiologist at Cincinnati Children's Hospital. And today I'm going to be talking about a software program that we have developed to address a need in analyzing relationships between place-based characteristics and health outcomes, while also maintaining the privacy of protected health information and maintaining reproducibility within studies, which we've seen as a big problem for, especially in multi-site studies. So we've developed a software program called DGAUS, which is a decentralized approach for geocoding and deriving community and individual level characteristics. These are things like census data, measures of community deprivation, airborne pollutants, green space, access to healthcare, and more. DGAUS uses a container-based approach, which allows it to work offline, and this maintains the privacy of the protected health information by never exposing it to the internet. And DGAUS also has a CSV in, CSV out format that makes it easy to learn for users with little to no technical background. So in summary, DGAUS is a secure, decentralized, and reproducible approach to solving geospatial privacy issues in multi-site studies. But further, it excels as a vehicle for making spatiotemporal exposure assessment models findable, accessible, interoperable, and reusable following the FAIR guidelines.
Hello, my name is Sabir Rashid. I'm a PhD candidate working with Deborah McGinnis at Rensselaer Polytechnic Institute. Computable biomedical knowledge is typically designed to support deductive forms of reasoning. Through think-aloud studies of clinical use cases in diabetes care, we have found that physicians employ additional types of reasoning, including abduction and induction. In particular, physicians interweave various forms of logic into dynamic reasoning strategies that mirror the select test model proposed by Stefanelli and Romani. To support physicians' cognitive models, we have chosen to design the clinical knowledge base using the cyclic steps of the ST model. We leverage semantic web technologies to encode each step of the ST model as an AI task that uses distinct forms of reasoning, such as abduction. In order to perform abduction using semantic technologies, we trace backward through graphs containing reasoning rule paths. We compose the AI tasks into a hybrid reasoning architecture, YIS, that can support particular clinical reasoning strategies, such as differential diagnosis, planned critiquing, and treatment planning. In doing so, we are constructing various types of novel reasoners that are compatible with description logics. We plan to evaluate the reasoning system and rule representation through the testing of clinical use cases that will determine whether system-generated insights align with what domain experts would conclude. Thank you.
Hello, everyone. I'm Rema Padman from the Heinz College of Information Systems and Public Policy at Carnegie Mellon University. This research is with colleagues Xiao Liu at ASU and Anjana Susarla at MSU. Imagine an individual who's newly diagnosed with diabetes and wants to learn more about it. Wouldn't it be great if the treating clinician can prescribe some videos for the patient to watch and learn along with their medications and testing orders? Well, YouTube has become the go-to source for many patients, despite the concerns about misinformation and disinformation. But it's not easy for the clinician or the patient to identify and retrieve high-quality videos from the thousands that have been created on diabetes. Our long-term goal in this research is to design, implement, and evaluate an automated, scalable, and generalizable recommendation system to improve patient education and public health literacy by curating publicly available YouTube videos for content that meets multiple criteria. Is the content medically relevant? Is it understandable? Is it accurate? Does it provide actionable guidance? And so on. The motivation is to help address the challenges posed by low health literacy of the public in managing the growing epidemic of chronic and infectious diseases by leveraging the vast repository of computable medical knowledge in YouTube videos on health-related topics, and making that quality content easily retrievable. We are developing an analytics pipeline that combines AI, deep learning, optimization, and natural language processing, and integrates all the extracted features into a multi-view recommendation engine to provide contextualized, just-in-time health education videos using diabetes and COVID-19 as early use cases. More details will be presented during the poster session. Thank you.
Imagine a world where you or any individual has easy access to evidence-based information and tools to support all the critical decisions and actions needed to achieve your health goals. For example, where tools provide the latest and best answers and resources relevant and helpful to you. And you can use these tools seamlessly on your own and with your care team. The current healthcare system doesn't address these needs well at all. And the result is that we're far from realizing the quintuple aim. That is where we simultaneously are optimizing health in an equitable fashion, improving patient and care team satisfaction, and reducing costs. We're not there yet because today's learning health system cycle, where we go from evidence to guidance to action to data and back to evidence again, doesn't work efficiently or effectively. And one of the main reasons for this is that we don't have the computable biomedical knowledge needed to make the cycle work properly. A large and diverse stakeholder group is developing a future vision concept demonstration where patients and care teams address clinical issues much better. They use tools that help make the right decisions and actions easier. Computable biomedical knowledge is the foundation for this future vision, enabling tools that make it easier to find and synthesize living evidence, process that evidence into living guidance that drives living clinical decision support interventions and other tools, the results of which generate more living evidence in a continuously improving cycle. Come to this session to hear more about how computable biomedical knowledge drives this future vision, and hopefully join us in this effort to accelerate progress toward the quintuple aim.
Hello, everybody. Thank you for allowing us to present at MCBK 21. We're deeply appreciative of this opportunity and the ability to collaborate, support, and benefit from the many initiatives underway at MCBK. I'll present our session today with Kenji Wong from ApraVita, the ApraVita Knowledge Studio product manager. I'm Chief Informatics Innovation Officer at ApraVita, a member of the MCBK Steering Committee and co-chair of the Policy and Trust Subcommittee. We want to tell you why we're thrilled to present at MCBK 21. A key component of the MCBK vision is to support knowledge abstraction, translation, and specification at scale, i.e. to allow knowledge engineers to take biomedical knowledge artifacts through a progressive knowledge engineering process that captures and makes available reusable knowledge components, such as value sets, regular expressions, and defines, or libraries of subroutines, as well as supports testing against standardized reference test data sets, and a healthcare organization's own data to uncover hidden biases either in the test data, the local patient data, or algorithms and pathways themselves, and allow fine-tuning where absolutely necessary and justified. A demonstration of the ApraVita Vital Platform and ApraVita Knowledge Studio will be provided. The Vital Platform is an open knowledge management, execution, and delivery platform. It connects knowledge producers with knowledge consumers. It allows knowledge authors, that is, professional societies, measure stewards, content publishers, to develop computable biomedical knowledge on a secure cloud platform and provides delivery of knowledge-based apps and services to disparate EHRs and other endpoints. The ApraVita Knowledge Studio supports the HL7 clinical reasoning module using elements from FHIR Foundation, the computable practice guideline on FHIR standard, and HL7 CQL clinical quality language, and can also encode other non-standard logic in a generic clinical reasoning engine. The ApraVita Knowledge Studio supports authoring standards-based digital measures and e-pathways using CQL on QDM or FHIR data models, with OMOP coming soon. Non-standard knowledge artifacts may also be encoded. This technical demonstration will consist of 3 parts. Overview of the Vital Platform and demonstration of authoring a quality measure, a clinical pathway in the ApraVita Knowledge Studio, demonstration of provisioning of CBK to a recipient site as an app, and 2 examples of workflow integration into disparate EHRs. Thank you for the time to describe this to you. I hope to see you at our session.
Hello, everyone. My name is Gavin McStay. I'm an associate professor from Staffordshire University in the United Kingdom. I'm going to talk about Biomed News, which is a biomedical literature expertise sharing system, which is based on machine learning and expert curation. I am also the director of Biomed News, and I'm working in collaboration with Thomas Crickle of the Open Library Society, who is the founder of this platform. So For biomedical literature, there are approximately 30,000 abstracts that are released each week, and these come through via PubMed. So this is an enormous amount of information that is released each week, and it needs to be robustly processed so the relevant information is able to reach the relevant community and community members. So Biomed News was developed to tackle this issue, and it uses machine learning to sort abstracts for individual topic reports, which are based on all different types of biomedical topics. So the main features of Biomed News are to rank abstracts in order of relevance, and these are sent to topic experts each week. And then these act as selectors to teach the machine learning platform to then identify relevant articles for subsequent weeks. So Biomed News experts are found are all over the world. And we are looking to develop this platform further and grow it to include more experts and include more sources of biomedical literature, such as preprints. So thank you, and I look forward to talking with you at the meeting.
This work and prototype are part of the National COVID Cohort Collaborative in the service of what I call computable science, how to make computing manage the process of science. What we have today is management through documents. So as an example, inclusion criteria are written in text, but then must be translated into code for prep to research queries, then again for recruitment queries, and then again for analyses. In N3C, we are implementing the notion of a computable protocol based on the notion of an articulated protocol in Odyssey and based on the many methodology checklists such as strobe, record, and start RWE. A protocol object allows for defining criteria once, and then linking them to variable and other objects created through code templates that are reused across projects. This specification and linking is then used to generate a variety of reports. More excitingly, it also provides opportunities for analytic decision support, since statistical workflow standard operating procedures can be instantiated at the right time to the right person in the right way. This work is a prototype for an ecology of tools that will work together to fulfill the promise of open and computable science.
Hello, my name is Dr. Mario Teran, and I'm a medical officer in the Center for Evidence and Practice Improvement, known as CEPI, part of the Agency for Healthcare Research and Quality, or AHRQ. I'd like to take a moment today and tell you about the exciting work we are doing through a contracted partnership with the MITRE Corporation in a project called the CEPI Evidence Discovery and Retrieval Project, or CEDAR. The main goal of CEDAR is to make research evidence, like findings from patient-centered outcomes research, more findable, accessible, interoperable, and reusable, also known as the FAIR principles. Our center has compiled several repositories with evidence ranging from systematic reviews and clinical practice recommendations to clinical decision support. But these repositories were built independently and over time with different architectures, which makes automating discovery and retrieval of that content more difficult. CEDAR aims to make this automation possible and more fair by using health IT standards such as Health Level 7's Fast Healthcare Interoperability Resources, or FHIR standard. We are building a prototype reference implementation of an application programming interface, or API, and will be testing and piloting it over the next 2 years. The CEDAR API will allow healthcare systems, EHR and clinical decision support developers, and many others to access AHRQ evidence in an automated way and incorporate it into their own platforms for use by clinicians, patients, and other target audiences. We know there's considerable delay between when research evidence is produced and when it is executed in routine clinical practice. By working with stakeholders like you and others in the MCB community, we hope to accelerate this process through tools and platforms like CEDAR. Please drop by our virtual booth, take a look at some of our materials, and join us on Tuesday afternoon to ask questions and to see a demo. We'd love to tell you more, and more importantly, learn from you on how to make what we are building even more useful. Thank you.
Good morning. I am Andrew King from the University of Pittsburgh. I am an informatics postdoc in the Department of Critical Care Medicine. My poster is on computable case reporting for multi-center clinical trials and registries. Case report forms, often abbreviated as CRF, are used to report patient data back to clinical trial coordinating centers and to central patient registries. CRFs are typically manually completed either by clinical trial coordinators or data entry personnel who review patient records in the electronic health records and then fill out the CRF either on paper or using electronic documents. Automatic CRF from electronic records would improve efficiency, accuracy, reproducibility, and auditability when reporting data back to trials and registries. We present recommendations to enable automatic CRF. In contrast to manual CRF, where the electronic data is copied over directly into the CRF documents, when doing automatic CRF, we add in steps in order to enable the reproducibility, auditability, accuracy, and efficiency of the pipeline. This pipeline here is enabled through encodable models and computational code, computable code. Thank you, and please see my poster for more details.
Hello, everyone. The title of our presentation is a public repository to mobilize computable biomedical knowledge. This repository is online and reachable at cbk.pub. My name is Güneş Koru. I'm a professor of information systems at the University of Maryland, Baltimore County. The other authors are Abir Rahman and Sayyar Ram, who are my graduate students at the same university. Recently, the Standards Work Group under the MCBK initiative published a paper in the Learning Health Systems Journal about a metadata approach to help mobilize computable biomedical knowledge artifacts, which we call CBKs. This approach involves using predicates to express metadata for CBKs under 13 categories ranging from type to domain to purpose to evidential basis. These categories were created to make CBKs more findable, accessible, interoperable, reusable, and trustable. In the same paper, we mentioned that we look forward to further developing and refining the metadata categories and to learning more about CBK metadata from the real-world experiences of those who use CBKs. For this purpose, and to be able to post our own CBKs, we created an online repository which allows creating and maintaining public CBKs. There's perhaps a benefit to make some CBKs public and sharing them widely. After creating an account, users can create CBKs using predicates within the metadata categories suggested in the paper. In addition to support automation, we created an API accessible in 18 different programming languages. I encourage you to check out cbk.pub. You can explore the CBKs posted and you can post your own CBKs. For each CBK, there is a discussion thread to discuss the CBK itself or its metadata. Our plans include conducting interviews and surveys to assess the perceived usefulness and complexity of the metadata approach with the users of the website. We hope that the repository will be useful for collecting usage-based feedback, and in the long run, it will support quality improvement and research in healthcare contributing to learning health systems. Thanks for listening to the presentation. Please visit cbk.pub. Not hesitate to contact me via email at gk@drkoru.us, and I look forward to our discussions during the MCBK 2021 conference, which is coming up. Take care.
The modern drug discovery process routinely uses a plethora of molecular profiling technologies such as metagenomics, transcriptomics, and immunoprofiling to uncover underlying biological mechanisms in health and disease. These high-throughput omic technologies generate large data sets that can yield great value, but are limited by dimensionality. That is, they have many features of which only some are relevant, and heterogeneity, that is, they have different characteristics. Traditional single omics do not take into account the relationship between omic types, leading to a data generation to interpretation gap. Therefore, multi-omics workflows are imminently warranted to integrate measurements from different platforms in an unbiased and statistically robust manner. In this poster, we present OmicsFold, an end-to-end advanced general machine learning pipeline to effectively integrate high-dimensional and heterogeneous data from broadly varying methodologies across a consistent number of samples. OmicsFold has critical advantages as it combines statistical approaches, machine intelligence methods, and biological interpretability in a single framework. It is built on top of Mixomics and an established package and leverages linear multivariate techniques to project multiple independent lines of evidence into a common latent component space so that direct comparisons can be made, each block is weighted equally, and results are generalizable. After fitting a predictive model with appropriate validation, our approach also allows for selection to identify discriminant features that load onto previously identified latent components and explain an outcome in a biological context. Omicsfold also offers a suite of downstream options after the final model has been fit. Importantly, it generates an optimized ranking of discriminant features across blocks using a novel approach called block rank to help with prioritization, and also provides a multidimensional correlation network of selected features across all biological data layers to elucidate new targets, combinatorial biomarkers, and pathways of interest. Thank you.
Hi. In the AMIA 2001 symposium, we introduced the concept of a public, a model of clinical practice which combines human readable media, like clinical guidelines, with machine executable knowledge. A public has many potential uses, including applying the executable component to patient data to give patient-specific guidance or advice on their care. The technical advance that made public concept practical was earlier. It was a language called Proforma, an intuitive AI language for creating executable models of expertise, from data to rules, decisions to workflows, care plans to clinical pathways. And the syntax and semantics for the language was published in JAMIA in 2003. The power and versatility of Proforma, we believe, has been demonstrated in applications across healthcare by independent research groups and commercial providers, including more than a dozen successful evaluations and trials reported in peer-reviewed medical journals. The Open Clinical project was later established to provide a platform for developing and sharing publics at scale, providing the necessary software tools for creating publics and an open access, open source repository for authors to share their models for appraisal and adaptation by others. You can look at that at the www.openclinical.net website. We're now developing the Open Clinical platform to support what we presently call Patient Journey, an experimental e-journal that members of the Open Clinical community can use to create new publics and edit and adapt existing ones. A demonstration of this concept is accessible online, and we provide information to access that. If you're interested to review the demonstrator of Patient Journey or work with us on its development, or if you represent a medical or other publishing organization interested in building on the work of the Open Clinical project, please contact us. And that's very straightforward, mcbk@openclinical.net.
Hi, I'm Shruti and I'm a PhD student at Rensselaer Polytechnic Institute, RPI. Today, I will be presenting joint work from the explainability workstream of the IBM RPI Health Empowerment by Analytics, Learning and Semantics HEALS project. With our work, we hope to aid clinicians who often use interfaces populated by machine learning predictions, and in these instances, seek supplemental domain knowledge to make sense of the predictions in the context of patients they see. Specifically, we try to provide relevant context by a multi-method approach to make available actionable and patient-specific domain knowledge as answers to a set of pre-canned clinically relevant questions. We're focusing on the risk prediction of comorbidities of a chronic disease such as type 2 diabetes as our setting. In our approach, we use risk prediction models, post-hoc explainers, and natural language processing modules to contextualize three entities of relevance in the risk prediction setting, namely the patient, their predicted risk, and the post-hoc explanations for their risk. Together, these methods generate contextual insights for these entities, drawing from domain knowledge sources, including patient data, ontologies, and guidelines. And finally, these contexts are displayed on a clinician-friendly dashboard, such as the one shown on the slide. On the dashboard, We show a risk prediction bar for a type 2 diabetes comorbidity, chronic kidney disease, potential actions for the patient and their risk consistent with relevant guidelines, and important features that influenced the risk prediction. We also engage with clinicians to improve the clinical relevance of our approach. Thank you. We look forward to talking to you all during our poster session, and we're excited to hear your feedback and to discuss our take on knowledge-enabled explanations and contextualizations to aid clinical decision support systems.
Hi, everyone. My name is Ramona Bladea. I'm a third-year medical student working in the Heinz C. Proctor Bipolar Research Program in the Department of Psychiatry. I'd like to speak today about a patient with type 1 bipolar disorder in whom we track daily mood changes, sleep onset and duration, activity levels, and heart rate for 8 weeks prior to a hospitalization event for a manic episode. This patient is part of a larger cohort and study in whom we are tracking these and other factors. And this is because wearables and apps have been increasingly used in bipolar disorder to collect detailed, individualized, longitudinal data on patients, and which we hope could identify markers that can someday be used to detect oncoming manic and depressive episodes. Our own lab created and validated one such app for assessing mood changes called DigiBP. Recent studies have suggested that there may be synchronicity in bipolar patients between mood, sleep duration, and lunar illumination, which is a standard measure of total daily light exposure and varies throughout the year. And so in addition to the variables mentioned earlier, we also collected lunar phase data to further explore the possibility of synchronicity. This is the first case report to our knowledge to examine so many factors in the same patient. And some of our preliminary findings have included observing more positive mood changes near full moon dates and more negative mood changes near new moon dates. Sleep duration was also shorter during full moon dates. A drop in resting heart rate corresponded in timing to a rise in depressive scores and activity intensity levels only 2 weeks prior to the hospitalization. These findings so far support those of previous studies, but this is an ongoing project, and we are collecting longer data from a larger cohort to better assess these correlations.
Good morning. My name is Saidarshna Dantu. Today I am here with my colleague, Rohita Bhaskar, and today we're going to be presenting for sorting and presenting clinical trial results for public health practitioners, along with our collaborative team from the Medical College of Georgia, Biomedical Research Innovation Laboratory at Augusta University, Tanzania People's Defense Force, Kilimanjaro Christian Medical University College, Military College of Medical Science in Tanzania. Randomized controlled trials are produced exponentially and are placed in the highest level of prestige for practitioners. Thus, relying on automation in literature research has become an attractive option for practitioners. As stated by MCBK, it's no longer sufficient to represent health-related knowledge solely in a human-readable form. The rapid rate of scientific discovery, the growth of health informatics, and the increased importance of models and guidelines require health knowledge that is represented in a computable form, such as the use of artificial intelligence. However, artificial intelligence cannot find information that is not in publication and cannot retrieve data that is not published. Hence, our study attempted to assess the readiness of the data presented in clinical trial reports to be used in automated data retrieval. Our collaborative team collected and systematically reviewed a pool of HIV/AIDS management randomized clinical trial reports and abstracted practically relevant information, and finally analyzed the public health value of the collected information. Eventually, our sample included 97 RCTs, of which 32.3% were missing personal resources, 33.3% were missing material and supply changes, 42.8% were missing major equipment and building investment, and etc. Additionally, majority of the articles lacked clarity on whether the found data was significant or insignificant, while providing complex multivariate and graphic illustrations. In general, clinical trials are reported in a highly variable format, making consistent interpretation very difficult. Thus, artificial intelligence application development should shift from the retrieval to more complete and structured reporting of the clinical trial results. By structuring abstracts for automated research and public health improvement, trial results could most likely be sorted faster and easier. For practical and efficient implementation of these clinical trials by physicians, impact-oriented clinical trial reporting is recommended. Thank you for your time today.
Hi, my name is Jared Anzalone, and I am very grateful to be able to share this brief but important message about some best practices when working with de-identified data. As background, I am a clinical informaticist and PhD student at the University of Nebraska Medical Center. Over the last 5 years, we've built a strong contingency of local investigators who work on research projects within our de-identified clinical data mart. As this community has grown, we've received increasing requests to extend the utility of this resource by supplementing with additional data elements not available in the EHR. Key among these is the inclusion of social determinants of health measures through location crosswalks, which can then be made available at the patient level. Some examples we've deployed locally include the Rural Urban Commuting Area Codes, or RUCA, and the BIRD Index, which is a socioeconomic index. While these measures are typically not identifying as they capture large geographically dispersed groups, deploying them within the context of a HIPAA-compliant de-identified data mart requires very careful adherence to the approved methods for de-identification. By making more than one of these measures available in combination with other measures of location, including state and 3-digit zip code, it becomes possible in certain circumstances to re-identify more granular units of location. This is a risk to HIPAA privacy requirements, institutional standing, and patient trust. In this project, we described this problem using a specific location-based index to show how easy it is to re-identify zip codes in certain circumstances. We describe how we overcame this, but the thrust of this project is to make others aware of the issue and embrace caution while working with data across de-identified studies. So with that, I thank you for your time and I hope you enjoy the conference.
Hi everyone, my name is Adil Ansari. I'm a knowledge engineer with the Krembil Center for Neuroinformatics at the Center for Addiction and Mental Health. We're a hospital located in Toronto, Ontario, Canada. So over the past 3 years, we've been building up our knowledge graph for both clinical decision-making and research usage. Our knowledge graph now contains structured and unstructured data, including clinical assessments, EHR information, clinical notes, lab data, and more. So during the MCBK presentation, I'll be going over how we have modeled the structured and unstructured data using the HL7 FHIR specification. Also, the knowledge graph itself is built on a tool called Blue-Brain Nexus. It's an open source tool, and during the presentation, I'll show a short demo of transforming source information, writing it to the knowledge graph, and then querying it using Sparkle and Elasticsearch. Finally, I'll touch on the next phase that we have at CAMH, which is how we plan to write back the analysis researchers are doing from the knowledge graph data, so that this data flows back into the knowledge graph and we have a continuously evolving knowledge graph for clinical and research purposes. During each of these sections, I'll be explaining how the process and the results help us adhere to the FAIR data principles, as well as our own governance policies. So that's all. I hope to see you all there and looking forward to the discussions. Thank you.
Hi, I'm Joanne Dane-Bostel from Computable Publishing, LLC. I have also been involved with the COVID-19 Knowledge Accelerator and Evidence-Based Medicine on FHIR efforts. And as you already probably know, Fast Healthcare Interoperability Resources, or FHIR resources, provide a standard data structure for electronic health records. The EBM on FHIR project is evolving FHIR to provide a standard data structure to represent scientific evidence. We make evidence-related FHIR JSON resources available in a platform called Fast Evidence Interoperability Resources, or FEVER. Many folks from these global projects have helped us to test and optimize the tools on our FEVER platform. I'm here to introduce a technical demonstration of that new platform at fever.net. You can see the link on your screen. The FEVER platform provides tools for making scientific knowledge findable, accessible, interoperable, and reusable. FAIR. You can use our platform to create FHIR resources in JSON format, including citation, evidence, evidence variable, and research study resources. Perhaps most importantly, all of this can be done without any coding expertise. You can use Citation Builder, Evidence Builder, or Recommendation Builder without having to see any JSON. The tools in our platform will also convert data from some other systems into FHIR resources for you. You can enter a PMID from PubMed or an NCT ID from clinicaltrials.gov, and the tools will gather all the data without any further editing on your part. We're coordinating with the Agency for Healthcare Research and Quality Evidence-Based Care Transformation Support, or APPS, to create a recommendations viewer and builder to show how automated data exchange with a recommendation survey browser can mobilize computable biomedical knowledge. We're looking forward to the opportunity to fully demonstrate what our platform can do. In the meantime, please visit fever.net to look for yourself and bring any questions to our demonstration. Thank you.
Hi, I am Mohammad Afzal, Assistant Professor in Sejong University, Seoul, South Korea. Today I'm here to present about FHIR framework for igniting biomedical knowledge. Management of biomedical knowledge is necessary for scientific communication, educational and other healthcare processes and decisions. But the problem is biomedical knowledge is diverse and comes in various forms and formats. More to it, currently, this knowledge is managed in large shareable value units such as documents, which creates hurdles in interoperability as well as compatibility. We propose a model that supports smaller shareable units, such as, for instance, where we want to share effect estimate. This smaller, understandable or meaningful information can be shared in the form of smaller unit, which we call in HL7 FHIR standard resources. So we propose this framework to support such kind of communication. We identify 8 very well-known and accepted processes coming from knowledge community, KMS, knowledge management system conceptual framework, which include the most important one is knowledge discovery, knowledge creation and modification, knowledge representation, knowledge translation and dissemination, as well as storage and retrieval. Within each of these 8 processes, we identify the principal 3 elements: people, technology, and contents. We believe that our proposed FHIR framework will increase the mobilization of computable knowledge framework because smaller unit supports the findability of precise information about our health, and this is the future of biomedical knowledge. Thank you very much.
Okay. Wonderful. Thank you so much for those terrific lightning presentations. It's great to see an overview of such a diverse body of work. I'll encourage everybody to look at the posters. You can see them on the Hopin platform now. At any point, go in and see the slides, and then we'll have our poster session at 5 p.m. Eastern today where you can talk with the individual authors and have some discussions. My role now is to introduce the break. We will be taking a break now until 3 p.m. Eastern time. During the break, I want to encourage you to look at the posters and take advantage of the 2 networking sessions that we have to chat with folks and meet other participants. We've been seeing some activity in those throughout the meeting, and that's great. That's great to see. When we come back from the break, we will have our panel on implementations of CBK around COVID-19. We'll have a tribute to Dr. Milt Korn, and then we will also have a panel on global perspectives. So we'll break now until 3 p.m. Eastern time, and we'll look forward to seeing you then for the rest of our program.